register, and I don't know what I did. In order that you to decide whether you evaluate or not. Oh, I'm discovering something, sorry. And so we will finish like 11:05 or something like that, so that you can have time if you want to evaluate the course. Okay, so that's the announcement. And a second announcement is that by Monday, I will provide both feedback for the graded exercises that you uploaded from the lab and the course. It's not that I haven't seen them, I've seen them, but I'm preparing like feedback and special instructions asking you to complete or to do some modifications. So this is why it's taking a little bit of time, because it's per person feedback. But I think that this is important, because in that way you can measure what you could do. You have comments on the strategy that you adopted, and then I will also, well, you will also know how to enhance your designs, etc., and then complete them eventually with further aspects. So that's the two announcements. And so today we are going to start a new topic. And so we are going to start moving from storage, yes, into processing. Yes, please, Mauricio.
Yes, teacher. It's just that I just arrived and I
Yes.
didn't hear the
The
announcements.
announcements that we are
Yes.
going to finish, I think, 5, because you, so that you can have time to evaluate the course and the lab, if you wish. And the second is that from Monday you will start receiving feedback on the exercises that you uploaded. And I was explaining that it took time because I will ask you to enhance and do extra work for both exercises and, well, it's per person feedback, but I was saying that it's important that we do that, because in that way you know where you are and what is necessary in order to complete your work, which is the idea of building your knowledge yourselves. So these were the two announcements. And then I said that we are starting a new topic. And the new topic is we are moving into data processing. So we've been working a lot on storing technology, and now we're moving into processing. And in order to move into processing, we have to have a look at two types of solutions. The ones that will help us do the management of the raw data. So I will give a very, very brief overview of existing technology that you can use in order to archive your data. And this is important because in many companies today, dealing with this archival is a kind of issue. So I suspect that when you will go and have interviews on positions that you can access to, it might be useful that you have some knowledge about this archival technology. But this archival technology will be also useful in order to study the infrastructure that we need in order to process data at scale. Okay, so from the point of view of the university, we are moving into data processing at scale, but in the, we can say, industrial point of view, I will give some hints, even if we will not go into deep matters, because I well, the course is not about this, but so that you have knowledge on this. So when you learn databases, you learn that the process that feeds data into the database management system, whatever it is called ETL. Okay, so extraction, transformation, and loading. Okay, and this DTL, in fact, is a very big issue, particularly in companies, because data is produced in all over the different offices and by the different sub-organizations in companies, and the idea is that if we as an organization are not aware of what information is being produced and shared across the assets of the company, we are going to lose resources and particularly money. Okay, so it is necessary to adopt a data curation strategy in order to exactly know what is archived in our servers, whether in which situation, in which status of processing the data is, and who has access to this data, and whether it is possible for the members of the organization to have access to this data. Okay, and in order to maintain this, there is the notion of data curation, which comes from from art. You remember that museums have a huge a bunch of art pieces, and the curators, what they do is know which the pieces are, have information about them, the cost, the content, everything possible and imaginable to say about each piece of art. Well, the idea is that we do the same, but for data. And the objective is to propose solutions and protocols that provide the right data for the right use and, in fact, in the right moment. Okay, so questions that have to be answered in order to deal with this archived data. So I'm talking about raw data, okay, brutal, only digitalized data. So is the data clean? If not, what can be done in order to clean it? Or is it important or necessary to clean it? What information is available in these collections, in these data collections? Are there relations between data collections which could be exploited in order to better predict some situation in the organization? And what are the update rates, and in what way does this affect the collection? Okay, so it's all maintenance of this bunch of data that that lays in the storage of an organization. And so I have a nice animation, but this doesn't matter. So the definition of data curation is data management through a life cycle of interest and usefulness. And the idea is that you are going to enable discovery and retrieval. So questions would be, do we have data necessary to predict earthquakes in Cholula? Or do we have enough data to figure out whether there are petrol resources in the south of Mexico? These kind of things. Then we have to maintain the data, and there is the notion of data quality that is again a big issue in the market today. The idea is to know the status of the data, the quality of the data, in order to know what are the investment that we have to put in order to use it. Then is there added value on this? And the idea is that data curation must add value to the maintenance of the data. And of course, the idea is that this data shouldn't lie there. It should be reusable in time. Okay. Otherwise, we are losing storage space, and since we are in pay-as-you-go settings, we are losing money. Okay. So data curation, there's always a workflow behind almost all processes. So data curation means harvesting the data, which means collecting the data, vetting the data, like in mining, like in mines, selecting which is the right data to keep, then deciding, once we know this, deciding where to preserve the data, what are the metadata that we are going to choose in order to describe the data. We saw, for example, in Kaggle that there is a lot of metadata about licenses, about topic, about provenance, etc. In Kaggle, they made a decision saying that this is interesting when people want to perform data science queries. But data is not only participating in data science queries, it is participating in many other activities within the decision and the functioning of a company or an organization. So the idea is to determine which is the right metadata in order to describe it. Then there is a problem of grooming, which is maintaining and processing, etc., and then provisioning. Okay, so this grooming and this provisioning is part of the exploitation. So for your, just to attach this to connect it with reality, for example, there are companies today, there are startups that focus on grooming and provisioning of data collections. Okay, so you can make business out of this because this requires resources and this requires a lot of processing, which is the topic that we are going to start addressing in this second part of the lab. Anyway, okay, we select, etc., but an important and consuming thing and processing thing that we need to address is this extraction of metadata. Okay, so the problem of extracting metadata has been around in computing science for ages. Okay, so before the existence of social networks, people thought that who is going to add metadata to the data and who is going to accept adding metadata to huge bunches of data, for example, the data lying on the web. And social networks thought that, I mean, those that were promoting them thought that everyone can do this. And some communities said, but you are crazy. Who is going to accept tagging the data just for free? And surprisingly, we do that every day if we are social networks, for example, users. The fact of tagging people appearing in photographs, the fact of the system itself timestamping the data that we produce, associating it with geographical information, etc. So this is tagging, and this is done partially manually, and we have tagged a lot of data. But anyway, the idea would be to do that automatically and figure out whether this could be done automatically. So, for example, if you have, there is a project here in Lyon regarding smart cities. and they collect a lot of information. It's called Grand Lyon, and the idea is that within the city, you collect data about bikes, about alternative transport, about the transport, about the traffic, about people living in the city, etc. And all these collections are shared in a platform, I mean, in a site on the web. And question is whether it is possible to extract many different metadata so that we could run the city automatically. So for example, out of know whether it would be possible to control the traffic lights automatically at a given situation, at a given status of the given day, moment of the day, etc. So there's a lot of work, academic and industrial work done in order to figure out how to extract this metadata. And another problem is a database design problem. So which is the right structure, and how can you best define the metadata that you are going to associate to the data? Okay, so many people in kind of the last 10 years, if you wish, thought that having DTDs or XML schemata was an interesting way of doing that, and there were many initiatives in order to define these metadata models. But today, since we are in the wild and we are in big data settings, the idea rather is that you never say which is the metadata that you can associate to something. You just try massively to generate this metadata and then enrich this metadata as the data are used. And so in such a way that at some point you will have a lot of metadata about the data. So this is the big change of perspective with regarding the fact that we have a controlled setting and now we are in the wild. So a lot has been done regarding quantitative data that we have seen practically in Kaggle. And I didn't insist when we touched Mongo, but in Mongo, particularly in Compass, you can have this. I think that we did. I did click, but I didn't insist it for more or less than in Kaggle. For every attribute that you have in a document, it will generate. In a document collection, it will generate the statistics like in Kaggle about the distribution of the values, etc., and also the structure of your documents automatically. So nothing has to be done, and this is useful when you want to make decisions on your sharding, for example, etc. For example, in sharding, you should remember, so which is the right attribute to choose in order to do sharding in MongoDB? Well, if you come and see the distribution of your attributes, for example, if you are willing to adopt an interval-based sharding strategy, you are looking for those attributes that have a normal distribution, for example. And so here you can have a look at the status of your database and know which would be the right estimate, which would be the right attributes to be used as key, sharding key, for example. And then if you do not have this, then you would rather decide to have a hash strategy. So you see, these quantitative metadata can help you develop a sharding solution for your database at a given moment of the story, of the history of your database. So, but you can go further, okay? And there are works trying to extract semantic metadata, okay? So what does it mean to say that the attribute employee, so this string, what does it mean, in which language is it represented, etc.? Is there a definition of the concept? So people try to go further and have a semantic approximation of the problem, and then you are going to try to make connections. And that, again, I always use the social networks because it's this happens in our daily life, is whether you can establish relationships among the entities. And so there is a lot in analytics that can be done in that way. And again, well, the social network always asks us about feedback in order to determine whether there are links or not, and there are semantic links. No, it's not the same thing to have followers than being a follower. It's not the same to having a acquaintance relationship rather than a family relationship, rather than a contact relationship, rather than a professional relationship. So these types of relationships are typed in the social networks and are deduced and inferred from the knowledge that the system has about ourselves and other users. And you can, it is important that for data processing, we are aware of which level of extraction of metadata we are looking for. Okay, so of course the starting point is that there is no metadata, so we have the raw data, and then we have to figure out how to extract the metadata. Then you have a level 2, which is partial metadata, that would be the structure of your collection, and then the quantitative measures, and then complete metadata would be to really have quantitative, qualitative, etc. metadata. And depending on this, you have different levels of curation, and you are going to implement different strategies of curation and therefore of data processing to your archival solution. And this, there is a problem we learned at the beginning of the course, that there is a big problem of variety in big data collections. Yes.
Teacher, could you explain again what is partial metadata and complete metadata? It's just that I didn't catch it.
Yeah. Partial metadata is that you do not have all the metadata possible that you can associate to a data collection or an asset, an entity. And complete metadata is, for example, partial metadata would be to have the structure like in Compass or in Kaggle. You have the structure of your data collection, and you have the quantitative estimation of the content of the data collection. You don't know the meaning, for example, of the attributes. You don't know the intention of the data collection, and then of course the description that you have associated in Kaggle, for example, you do, but in MongoDB you don't. Okay, but anyway, there's something missing in order to have full control of the data collection, and this would be partial. In fact, we are always in partial. And then complete would require to have everything that can be said about a data entity. Okay. So, for example, in the relational solution, we do, because we have an understanding of a full understanding of the mini world that we are represent, even if it's a simplified one. But once we are in the wild, we don't. And okay, so but basically it would be to have both structural, quantitative, and semantic metadata associated to a collection, and there you could say that is less partial than, it approaches more into complete. Did I answer?
Yes, yes. It's just that the level 3 has semantics, the meaning of the structure,
Yes.
right? Okay.
Yeah. Yes.
Okay. Thank you, teacher.
Good. And so, since again we are in the wild, and if you imagine that you do not have only one collection, but many collections being produced, and some with a lot of metadata, with no, with etc., and you are going to archive that in somewhere, you can end up with what we call a data swamp. Okay. So there is really a lot of data collections that we are no longer aware of what we have. This can happen, for example, in our computers or in our hard disks. You suddenly produce many, let's say, all the photographs that we take. And suddenly, since we do not name the files, etc., we end up with huge amounts of images that we never know what they are, who they took the photos, whether they are duplicated or not. It's a swamp, it's a mess, okay? So this is the first thing that data curation wants to avoid, and any organization wants to avoid. Okay, ending up with data swamps, and in fact, what they are looking for is to build what we call today data lakes. Data lakes are non-multidimensional, huge data warehouses. Okay, so you have learned about data warehouses, but the version that you studied regarding data warehouses were historical data, huge volumes of data, but represented in a multidimensional manner. Okay, so full control of all these huge bunches of metadata of data. Imagine that you do not adopt the multidimensional schema, and that you just let the data come as there is, okay? But that you generate the right metadata in order to know that this portion of the data warehouse deals with data coming from, I don't know, in an organization, from the client's office. The other comes from the online workshop process, etc. Okay, so you know where it comes from, it's organized, it's classified, but there is no generic multidimensional schema that has a representation of all this content. Anyway, since you have knowledge of this, you are creating a data lake. And when people will come and ask whether we have data about A or B topic, you will query the data lake, and the data lake will put you in contact with all the data that refer to the topic you are looking for. Okay, and today many vendors, and particularly cloud vendors, provide data lakes solutions. Okay, so that organizations can work with their data collections and manage them correctly. Yes, Alexander.
Thank you, Doctor. So I wanted to ask that the difference between a data lake and a data swamp was that, say, because a data lake can contain inexhaustible amounts of raw data, what would differ the two is that data swamps are unorganized, or is the
Right.
what you name about being untagged, or
Yeah, they're not tagged, they are nothing. Nobody tags anything, it's just there. Whereas in the data lake, data are tagged with metadata.
okay. Thank you very much.
You're welcome. So you have the data lake, and then of course you always have the data lake management system, where you will have all the operations, the API that will manage your data lake. So you have the definition there. It's a centralized repository, centralized in a logic manner, okay? No one has centralized data today. So of course, behind you have a distributed physical architecture, but the notion of lake is one, okay? It's like Oracle, one thing, even if it's distributed behind. So containing virtually inexhaustible amounts of raw data to be analyzed. And again, another difference with respect to the data warehouse is that the data warehouse, since we are building the multidimensional schema, it has been transformed. I mean, the data has been transformed into the into the schema, into the multidimensional schema, whereas here, no. Okay? Even if you have metadata, the content, I mean the data, do not cope to any specific structure different from the one that it initially had. And then you can fish in the lake, as I said. So in order to fish in the lake, you should have APIs. That can help you explore your data collections. Then, depending, of course, on the solution, you can have very simple phishing, querying APIs, or very complex one, and also depending on the type of metadata that you have. If you have level 3 with semantics, etc., of course, the type of exploration that you will perform on top of your data lake will be much more advanced than the one that you would have if you just only have quantitative, for example, metadata with some tags. This is the example, the clear example is Kaggle, when you have the data lab and you have the all these bunches of data collections, you can do a queries as information retrieval, no keyword queries, and then it helps you explore all the data collections that they provide. So it's a very simple exploration technique. Whereas if you had something else, I'm trying to, I will show you later on systems that use semantic web. So in the semantic web, for example, do you know the Microsoft Academic Graph? It is an explorer that helps you retrieve bibliography. And so there you have a graph of people connected among each other that publish academic papers. So there it is a data lake, but the exploration is out of a graph, and in some versions you have really the graph and you clicked on the nodes in order to see communities of people working in some area, etc. Okay, so there, since it is really, really curated, well, you have very advanced exploration APIs. So, for example, if we go back to the smart city story, we could say which are the available green transport modes in the city, or which are, in fact, which are the available green transport modes in the city, which are the collections that are related to available green transport modes in the city. That would be the right question rather than the one shown there. Okay, or which are the attributes used for modeling transport modes? You see, it's more about the structure, about the distributions, etc., rather than the content itself. And then, as I said, depending on what you have behind of metadata, you can go with very complex or less complex querying. Particularly, well, there are data structures called ontologies that represent semantics and that can be used in order to go through the semantics. But this is not the problem of the course here, it's just an example. Now, well, this is very nice, but what we are interested in this course is what is behind. And behind, there is very interesting things that bring us back to the matter that we are studying here. There is a lot of data preparation in order to build this kind of solutions, meaning data labs, meaning data lakes, meaning data warehouses, meaning data collection stored in NoSQL systems. Okay? In all these cases, there is a first aspect to consider related to harvesting the data. Starting from harvesting, since we are talking about, at scale, huge volumes or high velocity, we have to deal with parallel processing. Okay, so a very intuitive way of understanding parallel data collection is, for example, deploying bunches of sensors around a room or around the city, collecting data, for example, about, let's say, the city, about traffic, okay, and about people moving around the urban spaces, okay. So all these data collection is done in parallel, and which means that the ETL process that will bring the data from the source to the storage and archival infrastructure should be done in parallel. Okay, so many processors working at the same time together in order to put data in distributed storage supports. Okay, so imagine your sharding solution, but at scale. And so data are coming, and the sharding solution that you have starts distributing the data in a cluster of Mongos, and then behind the system is moving the data from one store to another in order to balance it. So this huge complex process is done in parallel. Okay. So question here is, how do we synchronize the harvesting of the data? How do we synchronize the feeding of the data into the storage support? And then how do we synchronize the fact that data is going back and forth from different nodes within a cluster in order to balance the distribution of the data and then ensure that behind there will be processes consuming it? Okay. So there are today systems that have been designed in order to do this process. We will study here some of them, those that belong to a very famous infrastructure today called Spark. Okay, so we are going to study two main technologies that are major in the domain today. One is Spark and one is Hadoop. Okay, so in the Spark environment, there are systems like these ones that are specialized in order to deal with this parallel harvesting. And but the problem is that this is wrong. Okay, this is the very initial collection of the data, and the thing is that we have to figure out. So this arrow, in fact, is you can open it, and there are processes inside. Okay, so there is the ETL process that again has to be done in parallel. So extraction, we are here. So this is the E. And then transformation, and there you should ask me, but you told us at the beginning of the course that we have to avoid transformation as much as possible. And you are right, but still we need to do some little processing from the digitalized version of the data into what we put into disk. And these even simple operations that we have to do in order that data go to the disk are part of the transformation process, which should be minimum because we are avoiding overhead. And this is done also in parallel. So particularly what we need is, we have seen that in NoSQL systems, everything lies in memory, okay? So, and one of the problems that we studied in the very last sessions was that we need to ensure durability despite of faults, okay? So we need to have the right data structures that help us to guarantee this durability. Okay, and solutions provide us with these data structures. And one very famous that looks like table, it's RDD. what you have here. So this we will have to study. We're going to study in the both in theory, but here we are going to practice on how these data are represented in these RDDs and which are the technical characteristics behind how is it implemented such that we ensure this fault tolerance in distribution, in data distribution. And every time we will have a look at these both major solutions coming from Spark and from Hadoop that I will introduce later on. Then we have preservation and description, where we are going to there really touch data processing. And so what is data processing? For example, in order to evaluate the distribution of a data collection, you either perform the processing in one node, or you can do it in parallel. So we are going to figure out how this processing is done in a parallel model. So this, I believe that you haven't studied parallelization, have
you? No, we haven't.
you?
No, not really.
Yeah, no.
Okay, so this will be the first change of paradigm, which is nice because this means that the course has some sense, is instead of computing the distribution in one shot, how do we do it in parallel? And how do we deploy these parallel processes so that they run faster than in a centralized manner? Okay, so this will happen in this part. And then there will be also, we will have a little view on NoSQL again, because in fact, all the operations that we do in querying are done in parallel, but they are transparent for us, okay? And why is it that? Because, you know, parallel programming is difficult. And it requires a lot of algorithmic knowledge. And not everyone, I mean, you are not going to ask a final user to have knowledge on parallel programming in order to perform her queries. That's not possible. And even in our case, some types of engineers, of computing engineers, might not be acquainted with parallel programming. And they are still engineers, and we still need them in order to implement solutions. So the idea is that many systems and many approaches provide transparency with respect to that. So we continue programming the way we basically know how to do in a centralized manner, and then there are transformations behind by compilation or by interpretation that produce parallel code that runs on the kernel of the system. So this is what happens, in fact, in NoSQL and NewSQL systems. So we will kind of open the box and see how does it look like behind the scenes. And then, of course, there is exploration, which is more or less what we did in the experimentation part in the last on Tuesday in the lab. Okay, so we were performing experiments that process data, and that, well, the one what we saw was based on statistics, but you can apply artificial intelligence, machine learning, and other numerical models on top of the data, okay? And there again, in order to do that, either you do it in a centralized manner, as you have numerical methods, no? The course you have already had it. Have you?
Yes, I think so.
And did you program the algorithm? I mean, the methods? You know, in my time, we did, well, of course we programmed, but there was a lot of things, there were a lot of things done on paper. But it was another time, and then of course there were projects where we programmed, but today many algorithms are already programmed in R, in MATLAB, etc. So I don't know whether you really programmed or you used the functions.
I think we did have to program it mostly from the ground up.
Okay, right. Well, if you have to program, well, I suppose that you did it in a centralized manner because there were essentially not a lot of data. Here, it's the same, but in parallel. Okay, so many numerical algorithms or operations done on matrices, etc., are those that are the classic exercises that we will have a look on in a parallel manner. Okay, and that will be included in our query processing in order to explore and exploit the data. Okay, so this would be this part. And so, as I said, in future sessions, what we will learn is that how to parallelize, and of course, where to deploy it. So I'm just going to provide a short example about a system that does curation. So the name is Atlas. I'm using this example because Atlas is quite a famous solution. It's just to provide you with a concrete idea of a system that deals with the metadata. Okay, so it's a metadata management service. Okay, so if you are looking for curation and archival management solutions, you are looking for technology that provides you with this type of functions. Okay, so that's what is important to bear in mind, particularly if you are going to the market and sell yourselves as engineers and probably for developing data management solutions in terms of archival. So you have the data collected from the web or whatever, and these kind of systems will provide generic metadata schemata in order to deal with the metadata of your data. And then they are based on type systems. Okay, so you are going to reason about, for example, the attribute address is of type string 34. The attribute age is of type integer, from this level of metadata representation, and this you are going to represent as a schema. Okay, and the system, what it provides is a type system that will let you define the metadata that you want to associate to your data. And from the architectural point of view that we have been studying here, well, I'm talking about a service, so I'm talking about cloud-like, even if some of them do not lie on the cloud, or yes, it depends, but they are designed as services. Remember that when we talk about a service, we are talking about a hardware or software entity accessible through an API. Okay, so you have these APIs, and normally in many cloud solutions today, the type of protocol and architecture adopted by services is REST. Okay, so to make it simple, the methods and the operations that you are going to call from the API are embedded within the HTTP protocol. Okay, and so you are going to use this protocol in order to call your functions. And it is also based on, that's when you interact synchronously with the service, and it is also possible to interact asynchronously with the service, and in that case, you adopt a message-oriented setting, okay, a message-oriented protocol. Again, something that you, I mean, if you didn't learn in distributed systems, I think that if you have time in parallel, we might touch this, but we cannot touch all the computing again from A to Z in the course, okay? But one thing that it would be important is to get acquainted with microservices, because these microservices work on message-oriented settings. And so these type of architectures are popular and use these message-oriented solutions in order to make components interact within each other, between each other. So the generic metadata management architecture would look like this. So you could have data, and then you could use, for example, stores as the ones that we have studied. Well, here is HBase in Atlas, but you could have Mongo or CouchDB or whatever here. And so you have this underlying storage support, and then what Atlas provides is a layer called Janus Graph that will organize in a graph manner the data that are lying here. And in order to do that, you would have two types of services, the one that ingest and export the data, the type system that deals with the representation of the metadata, and then the graph engine that will help explore the data. And this is the core kernel of such a system. And again, I'm talking about Atlas, but any other archival system would look like this. Then you have integration API. So you have this messaging layer and API layer in order, as I said, to interact either synchronously or either asynchronously with the system. And then on top of this, you would have many metadata sources and applications that will manage and query and maintain the metadata that you will have here. Okay. So it looks a lot as a data management system. You have the three levels, etc. They are revisited, considering that you do not have a pivot data model, and that what you are dealing with is metadata that you explore, and that on top of archived data collections. So it's a kind of simplified version of a data management system with very thin levels, okay? And of course, you do not have the physical level behind, okay? Your physical level is a data management system, in fact. You remember that there are three levels in the ANSYS Spark architecture, right? Do you remember the three levels of the ANSYS Spark architecture?
Yes. Well, right. Sorry, the what? The
ANSYS Spark architecture. ANSYS Spark. Fundamentals of relational database management system, the standardized architecture of any relational database management system is called the ANSYS Spark architecture, and it has three levels. The physical level with a set of index structures that help you organize the data on disk. The logical level that provides with a data model, knowledge model. For example, in relational is the relational model. That means that all the data that you are going to export to consumers will be represented as relations. And then the external level that provides, again, with another model. It can be the relational, or it can be XML or any other model. And this represents the external views that consumers of the data have with respect to their application requirements. So here you have a kind of ANSYS programming of three-level architecture where, but instead of having the disk explicit, like in a relational DBMS, you have here a data management system. So this one has the three levels, but it's organized. I mean, it's a black box that serves as disk, these ones. So this would be the physical level. Then the logical level, it's only a type system. Okay? It's not a data model. A type system is like the type system that any programming language has. Okay, so it's a data types that we can use in order to represent the data. So this is a type system with the related operations. And so this is this. And then the external thing, well, this is an intermediary layer that helps communicate with the system. And then you would have here there is in fact no external system, external layer. Okay, so you only have two levels, the logical and the physical, which is not a real physical level. But anyway, it has this two-level architectures. NoSQL stores also have two levels. Okay, this is why they scale, because we are interacting almost all the time at the level of the disk. The logical level is very thin. Okay, clear? More or less.
Could you repeat which levels does this architecture have? You mentioned physical and another one.
Physical, logical, and external. The
Okay.
ANSYS part. And here we only have physical and a kind of physical and an external and logic. This story of
Thank you.
ANSYS Park architecture is very important. Huh? This is a glass door question in interviews. Okay, and so well, you have this, blah, and then it can become very much more complex if you open the box, and you can have there now you know you can have a polyglot storage solution behind. Okay, not just one system, but a polyglot version of this. This will be the storage backends. Then, since you want to go fast, you could have external indices backends that will provide, organize the metadata associated to this. The metadata will act as an index, a semantic index. And then you could even have OLAP solutions where you provide multidimensional representations of your data and you explore them. And these parallel processing solutions, when this grows a lot, then you need to go parallel and have these cartridges in order to process in parallel and ask OLAP or OLTP. You know what OLTP means, right?
Online transaction processes, right?
Processing, yes. And OLAP would be for analytics, no? Online analytics processing. Right. So anyway, in both cases, since we are at scale, they need to be executed in parallel, and we would have these parallel processing solutions. Gremlin is the generic action of graph querying. Okay, so it integrates, for example, Cypher and other languages and intended to query graphs. This is Gremlin graph. But anyway, they rely on these parallel processing cartridges that deal with the operations on top of the raw data and on top of the metadata. And you have applications exploiting this either on OLAP ways or in OLTP ways. So this would look like that if we open the box. And then, of course, you have the REST API with CRUD operations, etc. The classic APIs that we know now thanks of the use of MongoDB and Neo4j. And so then you have, of course, different layers of representation. So the kind of exercise that we made for polyglot persistence is more or less like that. So you have the UML representation of your mini world, then you have a representation or a partial representation of your data in some data model or in several data models, and then you can build on top of it tabular solutions in order to query and view and analyze the data. So it's always the same revisited in order to address different problems and different types of data management requirements. I'm not going to go further into the details of the types that Atlas provides, but what you have to bear in mind is that if you are looking for a metadata solution, you have to think about the architecture with the different levels, the three that I have mentioned, whether it is possible to have parallel execution cartridges in order to process at scale, and then which are the data types that we can use in order to represent the metadata associated to the data that are archived. Okay, these are the three elements that you need to look for in any solution. So with this, we are ready. So if you can see, so here there were examples, but they are not very important. We are ready to start digging into a parallelization. So for parallelization, we will have to rely on a distributed storage system. So we are going to start learning again computing. We are going to start with the file system, but in a distributed manner, and then we will learn how to use this in order to process in parallel. And this we have already seen. And with programming, okay? We will not have query languages for doing this. So we will program our solutions. And of course, on the cloud. Okay, so tomorrow what we will do is we will start understanding how do we deal. Do you use streaming solutions for example, for getting films or music, peer-to-peer systems? Well, if you don't, and if you're curious, these are the systems, the file systems that really scale in reality. And the idea is that we figure out how do they work in order to scale and that we can retrieve in a very smoothly manner content. Okay, so this is the very underlying element that we need in order to process in parallel. That's what we will learn. Okay, so I'm going to stop here because, as I said, I must give you time. This is not my choice, this is the university choice, that I have to give you time so that if you decide, you can evaluate the course. And so I'll see you tomorrow for more and finally parallel things. If you do not have questions before we stop the session.
No, all good, teacher. Well, I don't have
Well,
questions.
good. Yeah, today it was like blah, blah, very blah, blah. In general, when there's blah, blah, it's less challenging. Okay, so I'll see you tomorrow. And in the meantime, have a nice Friday. Thank you. See you tomorrow. Yes. Bye-bye. Thanks.
Nice.
Bye. Nice Friday.
Thank you, doctor. You too.